Well, hello again. I'm going to talk about viscosity and Poiseuille's law. So up till now, we've been talking about perfect fluids, fluids that don't have friction in them or don't have viscosity. So what is viscosity? Viscosity is internal friction in a fluid. We're going to look at some significant consequences of there being friction in a fluid. A couple of other definitions for us, something called laminar flow. Laminar flow. This is smoothly flowing fluid where the layers do not mix. So if you were to throw some dust on the fluid and watch the dust move, you would see the particles of dust just moving smoothly along like this. This is to be contrasted with something called turbulent flow. And this is fluid flow characterized by swirls and eddies that mix layers of fluid. Fluid flow characterized by swirls and eddies. An eddy is a little vortex that mix layers of fluid. So this is kind of hard to draw, but there might be a little swirl, there might be a little vortex like this. So if you threw your dust down in your fluid, it would just get all mixed up in the path of the fluid. So the fluid might be trying to go this way, but all the layers would get mixed. If you threw like red and blue and green dye in, you'd get all the colors mixed up together as the fluid moved along. That's turbulent flow. This sometimes this is bad. The turbulence behind cars and trucks and airplanes causes you to lose energy and makes them less energy efficient. Sometimes this is good. Sometimes you want things to mix, and if you want things to mix, then you actually want turbulent flow. But now returning to viscosity. How do we describe consequences or even describe viscosity? This friction in a fluid. We'll think about it this way. Suppose we have a plate, like suppose just a metal plate like this, and up above it we have another metal plate. And between the plates, we have a fluid. So in here, there's fluid between the plates. And this upper plate has area A. This lower plate is just fixed in space. And we push on this plate with some force so that it moves with some constant velocity, v. And we want to characterize how hard we have to push to get this to move with this constant velocity, v. And how hard we push depends on some things like how big this plate is, depends on how far apart these plates are, depends on how fast it moves, and it depends on the viscosity, depends on how much friction there is in the fluid. If this fluid is honey, this is going to be very hard to do. If it's water, it's probably going to be very easy to do. If it's oil, it's going to be very easy. So it depends on what the fluid is, and that's where viscosity comes in. So this, how hard you push is pretty straightforward. the force depends on the area. The bigger the area is, the harder you have to push. The velocity, the faster it goes, the harder you have to push. Inversely dependent on L, as this plate gets further and further from the lower plate, it gets easier to push. And this proportionality constant is the viscosity. That's where the material dependence comes in. If you put different fluids in, you get different dependence here. You have to push different amounts of force. So this is called the coefficient of viscosity. Viscosity. So that's actually how where viscosity is defined in this equation. To give it units, we need to make the units work out in this equation. So we know the units here, we know the units here. So the units of viscosity, so I'm going to use brackets to represent units. The units of viscosity have to match here, so they have to be the same as the units of force times length over area times velocity. Force over area is Newton per square meter. We've seen that before. Length over velocity is meter over meter per second. Newton per square meter is a Pascal. We just saw that. Meter over meter cancels. 1 over 1 over seconds is seconds. So the unit of viscosity is a Pascal second. So its unit is a Pascal second. That's the SI unit of viscosity. Another very commonly used unit is a millipascal second, and that is a centipoise. And that's a unit that occurs so often that I needed to tell you about it, because centipoise is just very commonly used. But the SI unit, the metric unit, the SI unit is actually the Pascal second. So, but 10 to the minus 3 of those is something called a centipoise. And for some reason we've become accustomed to using centipoise rather than 1/100th of a poise rather than poise. So here's our equation for viscosity. I'm going to do an example of that. And this actual geometry of one plate just stacked over another plate is very rarely, if ever, used, because very rapidly this plate would just vanish out of sight. What we usually use is a cylinder inside another cylinder like that, where this fixed plate would correspond to the inner cylinder, and the moving plate could be the outer cylinder. Well, I guess probably you make the fixed plate the outer cylinder, and the moving one, the inner cylinder, could be either way. So let me do an example like that. So here we go. Example of viscosity. We've got a cylinder, we've got another cylinder. I made that awfully big. Our equation says force is eta AV over L. And my question is, what force to rotate a cylinder like this, force to rotate a cylinder at, what I pick, 20 revolutions per minute, RPM, with 900 centipoise glycerol water solution between. So 900 centipoise glycerol water between the cylinders. Let me give you our geometry here to match this equation. So the glycerol water is in here. Our L is here. I guess I called it little l earlier. And we're going to let this be 0.5 times 10 to the minus 3 meters. That's half a millimeter. So these cylinders are really close together. I'm letting this be 6 centimeters, letting this radius be 3 centimeters. What else do I need? I think that's all. All right. So eta is 900 centipoise times 10 to the minus 3 Pascal seconds per centipoise will give me 0.9 Pascal seconds, so that our equation works. So if you looked up glycerol water mixtures, they'd probably be given in centipoise. Our area is the area where the plates are in contact. So the area is going to be 2 pi r times L. So that's 2 pi times 0.03 meters times 0.06 meters. That's the area of the plates that are in contact. So that is 0.0113 square meters. And now I think we have, we need the velocity. Velocity is the velocity out here at the tangent, where this thing is spinning around like this. One cylinder spinning like that. So velocity is r omega. That is 20 revolutions per minute times a minute per 60 seconds times 2 pi radians per revolution times the r, which was 0.03 meters. So the velocity of the plates is 0.0628 meters per second. So now we've got everything. Force is eta AV over L. Eta is 0.9 Pascal seconds. A is 0.0113 square meters. V is 0.0628 meters per second. L is the gap, 0.5 times 10 to the minus 3 meters. That's 1.28 newtons. You said, why on earth would anybody ever want to do this? But you could conceivably need to do this in some engineering application. It's more normal that this is actually how you build a viscometer, that you would normally measure the force and solve for eta, so that you would find out, well, you'd put an unknown solution in here and measure the force and solve for, well, what was the viscosity of that solution. All right, so there's our example of viscosity. Now I want to show you an important consequence of fluids having viscosity. And if any of you happen to go into, say, an area of medicine involving cardiac circulatory system, I think you'll find this interesting. Excuse me. So this is something called Poiseuille's law. This has to do with volume flow rate. So Q is volume over time, so in cubic meters per second, where we're looking at flow through some sort of tube or pipe. could be an artery, could be a vein. We've got a pressure P1 on one end, a pressure P2 on the other, a length L, and it has some radius R. And Poiseuille's law says that the flow rate through that looks like the pressure difference, delta P, that's just P2 minus P1, times pi R to the fourth, and that fourth power is what's so important, over 8 eta L. That's Poiseuille's law. I've heard this pronounced different ways, by the way. I've heard it Poiseuille, Poiseuille, and various others. I've stuck to Poiseuille. Excuse me again. On a quiz, I would give you this law, by the way. You don't feel like you have to memorize it. Here's where the viscosity comes in. If there were no viscosity, you could get any flow rate through this. But this fourth power is what's so important. For example, if you cut R in half, this would be a 1/2 to the fourth. The flow rate would drop by a factor of 16. So let's do an example of this. Let's apply it to an artery that is partially blocked by plaque. So suppose an artery is partially blocked, so decrease its radius by 20%. By what factor does the flow rate drop? So I'm going to assume that your heart manages to keep everything else the same. Certainly the length of the artery doesn't change. I'm going to assume that your heart manages to work harder to keep the pressure difference the same. So just to be explicit here, before the blockage, here's what you had. Had an artery like this, had a radius R1, had a P1 and a P2, and you had a flow rate through it, Q1. After the blockage, and had a length L1, or length L. After the blockage, you still had a P1, a P2. Now it's blocked a little bit. So you now have an R2 that is 0.8 R1, because it's blocked by 20%, so 80% is left. And you've got some flow rate Q2. What I want to know is Q2 over Q1, the factor that Q2 changes. Q1 is delta P, delta P pi R1 to the fourth over 8 eta L. Q2 is delta P pi R2 to the fourth over 8 eta L. So Q2 over Q1 is the ratio of these. It's delta P pi R1 to the fourth over 8 eta L over delta P pi R2 to the fourth over 8 eta L. You see everything cancels with the R's. So this gives me R1 to the fourth over R2 to the fourth, which is R1. Sorry, this should have been 2 over 1. This is because I had the 2 on top. So that's R2 over R1 to the fourth. R2 is 0.8 R1. The R1's cancel. So I get 0.8 to the fourth power which is 0.41. So this tells me Q2 is 0.41 Q1. So Q2 is only 40% of Q1. So this means the flow dropped by almost 60%. So even though the plaque only covers 20% of the radius, if you looked at the artery end on, it used to look like that. Now it looks like that. You've lost almost 60% of your flow rate. And that's a consequence of the fact that the blood has viscosity. And notice I didn't even have to know the viscosity. Just the mere fact that it has viscosity has this enormous consequence. So we can't ignore it. And all their equations up till now ignored the fact that the fluid has viscosity, but that's very risky. You can't do that. Another case where this would be important would be in tubing. If you just come in and change the tubing on an IV and you change the diameter of the tubing, that makes a big difference. You can't change tubing diameters and just think you're going to get the same result. It doesn't. It doesn't give you the same result. All right. Well, as always, you can practice that in your in-class assignment and your homework. See you soon.